Good evening to all of you. Welcome to the session on analysis of compression member for the column section. It is the continuation of the previous video. In the earlier video also we have analyzed the column sections of different types of problems. Now in this session also let us try to understand how to analyze the different types of column sections. Let me take the problem. Here a single joist section of ISMB 250 at 37.3 kg per meter has been given with an effective length of 5 meters. It has been provided with additional plates of size 250 by 10 mm which has to be welded to the sides of the flanges as you observe it here. This is the 3D model that has been generated by the AutoCAD. We'll show you, we'll have a look on all these things in the video, in the 3D video session. We'll try to know about the different types of things. Coming to the analysis part, it is almost the same procedure as we have done it in the previous video. Let us note down the properties of the ISMB section of depth 250 mm, weight 37.3 kg per meter. Note on the area, the moment of inertia of the section, of the built up section. The total area of the built up section is equal to the area of the rolled section plus twice the area of the cover plate. We'll find out the moment of inertia about ZZ axis and YY axis. It's of these two things. Moment of inertia about ZZ axis, for the plates we have to apply the parallel axis theorem, where the moment of inertia of this section should be transferred onto the built up section. So we are going to apply this formula. It is Ig plus AH square. Ig is nothing but moment of inertia of this plate about its own axis, that is B dq by 12. A is the area of this plate. H is the distance between this plate and the built up axis of the built up section. We'll find out one by one. Ig, moment of inertia of the plate BdQ by 12. Area of one plate is 250 into 10 is equal to 2500 mm square. H is the centroidal distance between the two axes under consideration. The total moment of inertia of this built up section is equal to moment of inertia of the joist plus moment of inertia of the two cover plates. So about the rolled steel section, it is 5131.6, and the other one we are going to take it of the cover plates. We get the moment of inertia about ZZ axis of the built up section equal to 135.86 into 10 to the power of 6 mm to the power of 4. Similarly, let us calculate the moment of inertia about the YY axis. So since the axis is passing through the centroidal axis of the plates here, there is no need to apply a parallel axis theorem. We know the formula to get the about y axis for the rectangular plate. It is d b cube by 12. D is 10 mm, b cube is 250, db cube by 12 2 times. Now get the minimum moment of inertia. It's the least of Izz and Iyy. Iyy is the least. You obtained this value equal to 29.387 into 10 to the power of 6 mm to the power of 4. And let us calculate the minimum radius of gyration, which is under the root I by A under the root. It works out to be 54.89 mm. Now we'll go with the end condition of the column for the length. If it is given as slenderness ratio, we'll calculate, it is given as KL by R. The effective length is directly given as 5 meters. Find out the value of SR, slenderness ratio lambda. And coming to the buckling class, we know very well that for all the built up sections, it will be, we have to refer the buckling class C from table 10 of the code book. Looking into the table 9C of page number 42 of IS 800, let us get the value for the slenderness ratio equal to 91.1, the value of FCD. By drawing the table by interpolation method, we are going to get the value. For 90, it is 121 Newton per millimeter square, megapascals or Newton per millimeter square. For 100, it is 107. Find out the difference of these two. For 10, it is 14. And for 91.1, that is for 1.1, what is the value? Let us do it by interpolation. The value of FCD is equal to 119.46 Newton per millimeter square. The load carrying capacity is given by the formula stress into area provided. Stress is 119.46 into area of the total section is 9755 mm square. Therefore, we got a load of 1155.33 kilonewton. This is the load carrying capacity of the member when a flange is placed on either side of the column section. Now let us look into another problem where the plate of same size has been provided on the sides. It's welded like this, not on the top and bottom of the flanges, on either side of the flanges. It's been provided on the sides like this. Let us see what is the load carrying capacity, whether it will be more than that 1155.33 kilonewton or less than that. By placing at different positions, let us try to understand which one will take more load for the same section properties. So once again, we are noting down the properties of the ISMB section, like area, flange width, moment of inertia, the total area of the built up section is equal to area of the rolled I section plus 2 times the area of the cover plates. It is 9755 mm square. Now let us find out the moment of inertia of the built up section about ZZ axis and YY axis. For the ZZ axis, there is no need to apply any parallel axis theorem. About when you want to calculate about YY axis, we have to apply the parallel axis theorem for these two plates, transfer the moment of inertia of this plate from here on to the YY axis. There we have to apply the parallel axis theorem. Now for the ZZ axis, it's a moment of inertia of the rolled section plus 2 times B d cube by 12. B is 10, d is 250 cube by 12. It's 77.35 into 10 to the power of 6 mm to the power of 4. Similarly, get the value of IYY. As I said earlier, we have to transfer the moment of inertia of the plate onto the centroidal axis of the built up section by applying parallel axis theorem. 2 times d is 250 b cube by 12 plus the area of that plate into the centroidal distance of this is 125 by 2 plus 10 by 2 from here to here, multiplied by 2 so that 2 plates will be taken into consideration. Now we get the value of IYY 26.17. The minimum is 26.17 into 10 to the power of 6 mm to the power of 4. Get the minimum radius of gyration. It is root of I minimum by A. Find out the slenderness ratio its effective length to radius of gyration, it's 96.53. For this value, let us find out the FCD value from the table 9C, because the buckling class lies in the C. From 9C, page number 42 of the code, we'll find out the value of FCD for lambda equal to 96.53 value. Draw the table. Get for 90, it's 121. For 100, it's 107. The difference of that is 10. For 10, it is 14. For 96.53, what will be the value? It's 111.86 Newton per millimeter square. Load carrying capacity of this member is 1091.20 kilonewton. Now you find the difference here. In the same problem with the cover plate placed on the isoside of the flange plate, we got 1155.33 kilonewton, and here it is 1091.20 kilonewton. Almost a 65 kilonewton difference is there. So that type of connection means an I section with cover plate on either side of the flanges will take up more load than a cover plate provided on either side of the I section. Now let us look into the another problem, that is, three I sections are being joined together by I sections are joined together either maybe with the bolted connections or welded connections. Welding could be done here all along the length of the member, or boltings could be done along this. And this you can observe it in the 3D model session, where 3D views will rotate all the things and we'll see that how the connections have been made. Now the here quite different in calculating the moment of inertia. Try to understand this. Note down as usual, note down the properties of the section. For ISWB 450, note down the area, thickness of the web, the moment of inertia about ZZ and YY axis. It's for the individual member. All these properties whatever taken is for the individual member. From that we'll calculate the moment of inertia for the built up section. Total area of the built up section is 3 times the area of the rolled sections. It is 30345 mm square. Now to be careful here and understand the concept of calculating the IZZ and IYY of the built up section. Now whatever the I section we had here, these two are vertical and this has been rotated here. So IYY will become IZZ, IZZ will become IYY in this case. That is what to be understood. Now we got moment of inertia of the built up section about this. It is the moment of inertia of this two rolled section. It is 2 times of 35057.6 into 10 to the power of 4 mm to the power of 4. Plus the moment of inertia of this one. For this one, it is YY value will become ZZ here. This is a YY value of the individual section that will be taken here since it has been rotated. That will be taken as ZZ value. So you're going to take this IYY under the for the built up section as ZZ. This is what you should understand it. Just because we have rotated it, the YY value will become ZZ and ZZ will become YY. This value, whatever it is, it was ZZ value of the section. Since it has been rotated, as I said earlier, this value ZZ to be treated as YY here. That is what is important. The reverse case of this one. Plus 2 times the moment of inertia of these ij sections placed at certain distance away, that is equal to, by applying parallaxis theorem you are going to get it, 17067 point is Iyy of this value plus h square, area of this is known, it is 10115 mm square, into h square, the depth of the section is 450 mm, 450 divided by 2 plus Tw by 2 from the center of this. So it is 450 by 2 plus Tw by 2, will get h value, get the moment of inertia of the Iyy. Now get the minimum value of this moment of inertia, get the radius, minimum radius of gyration. Then afterwards we will calculate the effective slenderness ratio of the section, its scale by r. Effective length is given as 4.25 meters. The slenderness ratio is 27.62. From the table you have to get the value of FCD. Buckling class is same since it is a built up section. It's buckling class C. Get the value of FCD from the table 9C, page number 42. For 20 it is 224 megapascals. For 30 it is 211 megapascals. Get the difference. Get the difference for 20 and 27.62. It is 7.62. Let us find out the value for that. By interpolation we are getting as 214.09 Newton per millimeter square. Load carrying capacity of the member is FCD into area of total area of the column section, built up section. It is 30345 mm square. Now we get the load carrying capacity of the member as 6496.56 kilonewton. The safe load is obtained by dividing by factor of safety of 1.5. It is 4331 kilonewton. We will move on to the AutoCAD session, to the 3D model session, and have a look on the different types of columns. Then we will continue with the problem. In the 3D model session, let us try to understand the different types of built up sections. This is one of the type of built up section that has been provided here. That is an I section roll section has been connected by cover plates on either side of the flange, joined together by the bolted system as you observe here. This is one of the type of connections that we have analyzed, or it can be designed in the design problems. You can have a look. This is a foundation part, and with this things, study about all these things, we can study it in the slab based connections or in the gusseted based connection. Now I am analyzing in this session only with the built up section as you observe it here. This is a top view. Of the built up column. Rolled steel section, cover plate, and in turn connected by the bolts. Either you can go with the bolts or it can be connected with the welding on the at these edges, at the root radius. Sorry, toe radius. These are the toe radius position. This is the root radius position. And let us see that in the next problem, next view. This is what you are observing is the built up column with the cover plate. Joined together by welding, as you observe it here. I can zoom it out a little bit more and show you the connection, the welding connection that has been done throughout the length of the column. Here also you can observe it. Let me show you the top view of this one. This is the connection. What you can observe, welding that has been done. This is also a built up column. We'll look into the another one where the three high sections are being joined together, as you observe here. This is a plan as what you observed in the question there, elevation of this, the side view, and this 3D models are being generated only to make you understand the concept of the subject. And here either you can go with bolted connection as you observed in the previous problem, or you can go with welding on the corners at this edges. Any method you could adopt. Now let us try to understand some more problems of different types of connections. Let's look into the another problem where two channels are being joined together back to back, that is ISMC 350, and which has got an effective length of 6 meters. We have to find out the safe loading capacity. This is one part of the question. We got additional part where it says that two cover plates of 400 by 10 mm are to be provided on either side of the flanges of the channel section, and we have to find out what will be the load carrying capacity, how much extra load it can take. Now let us take the first case 1, where its channels are being placed at 200 mm center to center. Now we can note down the individual properties of the channel section and afterwards get the value of IZZ and IYY of the built up section, or if it is possible to get the value of IZZ and IYY with respect to this channel placed at 200 mm from the steel table itself or from the code, you can directly obtain the value. Now I'll look into this properties from the steel table, where for ISMC 350 at 200 we have got the properties. Note on the area of this, the radius of gyration about ZZ axis, and about YY, RYY, we have to look into 200 mm apart. The spacing of these two channels back to back is 200. For that it is given as 12.76 mm. The minimum radius of gyration is RYY. The effective length is being given as 6 meters. The slenderness ratio is effective length by minimum radius of gyration, it is 47.02. And buckling class, now we are used to this. Since this is a built up section, it lies in the class C. So by interpolation, referring into table 9C of page number 42 of IS 800-2007, we can get the value of FCD for 47.02 slenderness ratio. So for 40 it is 198 and for 50 it is 183. For 47.02 how much? and you're versed with all these things. You know how to calculate. FCD value is 187.47 Newton per millimeter square. The load carrying capacity of the member is 2007 kilonewton. The safe load is divided, you're going to divide this load capacity, you're going to divide the ultimate load or the factored load by 1.5, and that is equal to 1338.33 kilonewton. Take it as kilonewton here. Note on that. Now they will look into the second part, case 2, where additional cover plates has to be provided on either side of the flanges of size 400 mm by 10 mm. Like this, we have provided the cover plates at top and bottom or on either side of the flanges. Let us that how much load, extra load that can carry if you connect it like this. So the properties, it remains same for the I sections. Now we are not going to look into the radius of gyration, we are going to take the moment of inertia into consideration so that we will calculate the radius of gyration. Moment of inertia about ZZ axis for this built up column ISMC 350 is 20016 for ZZ axis, and for YY axis, which is placed at 200 mm apart, you are going to get here it is 17,469.4 mm to the power of 4. The total area is equal to area of the two channel rolls channel sections and the areas of the two cover plates. Let us find out the moment of inertia about the built up section, about ZZ. It is a moment of inertia of these two channels, plus by applying the parallax theorem, you are going to transfer the moment of inertia of this plate onto the built up section. It's 2 times BD cube by 12 plus area of this into the distance between these two axes. It is 459.43 into 10 power 6 mm to the power of 4. Now get the moment of inertia about YY axis. We know the moment of inertia of this two built up section directly. No need to transfer it. Additional thing is 2 times you have to take the moment of inertia of this plates about YY axis, it is dB cube by 12. D is 10, B is 400 cube by 12. The least moment of inertia is IYY. Get the least radius of gyration. It's 122.55 mm. The compressive stress is obtained here, has to be obtained from the slenderness ratio. Slenderness ratio is 48.95. Now since it buckling class is C, referring to table 9, page 42, by interpolation get the value of FCD for 48.95. So what are the things I am showing? It is a self-explanatory and you know very well how to get all these things. So FCD value is 184.58 Newton per millimeter square. The load carrying capacity of this member is 3457.55 kilonewton and the safe load is 2305 kilonewton. Now observe the difference. With the cover plate, the safe load is 2305 kilonewton, and without cover plate, what was the value? Just we'll have a look. We'll go back. and I will look on this one. Yes, it is 1338 kilonewton. So almost 1000 extra kilonewton load it's going to carry with respect to the cover plate that has been provided. So all these were the procedures. I am just running it fast, and now you can understand with the cover plate it can take almost 1000 kilonewton more. So that's the difference we wanted to make you understand while analyzing the problem. We'll go into the next problem, where it has been given with same two channels, cover plate only on one side. Now we have to look into the properties of ISMC 400 and get the breadth of the flange so that we can get the length of the cover plate, extra plate. On only one side we have provided. Now let us see the procedure of solving this problem and understand. So look into the properties of 2 ISMC 400. The area is 125.86. Moment of inertia about ZZ axis is 30,165.6. And for 300 mm back to back spacing, we get the moment of inertia equal to 39,202.6 into 10 power of 6 mm to the power of 4. From the single angle section, let us note down the depth and breadth of the section. Depth is very well known, it's 400, and the breadth of the flange is 100 mm. So I know now this is 100, so that I can get the length of the plate or width of the plate, whatever you call. It's breadth of the flange, BF, plus this cap, the spacing, back to back spacing, plus the breadth of the flange. It works out to be 500 mm, 100 plus 300 plus 100, 500. Now the size of the plate is 500 by 16. This is the total area of the complete section, built up section. Now we have to find out the centroidal axis for this one, which is very important. Note on the difference between the earlier problems and this problem, and do practice so that you can learn the different types and the ways of analyzing the problem. Let me consider an axis at the bottommost of the built up section, bottommost end. Let it be at a distance, the ZZ axis or the built up section be at a distance y bar. How to get y bar? We have studied all these things in the first year itself. In CG and MI chapter, how to get these values. Y bar is given by A1 plus A2. A1 is nothing but the total area of these two channels. A2 is the area of this cover plate. Y1 is the centroidal distance of this one channels, and Y2 is the centroidal distance of the plate from AA axis, reference axis. So we get the two channels area A1, it's given here, and let us find out the A2. Y1 is nothing but the center of this, is 400 by 2 centroidal distance. A2 is 500 by 16, and Y2 is 400. There's a distance from here to here, 400 plus 16 by 2. You'll get Y2. Get the value of Y bar. Substitute all those things in the Y bar formula, and it works out to be 280.83 mm. That's the centroidal distance. Now by applying parallel axis theorem, these two plates, we get XX, IZZ. So Y bar was from the bottom, it was 280.83, and from the top of the channel section it is 119.17. These are the properties that we had obtained earlier. Same thing we are writing here so that we can use it here in the problem. IZZ is the moment of inertia of this section about the central axis. So it is the IZZ of this one plus AH square. Area of that is 12586. h square is nothing but the difference between these two, this one and the center of this, that is 280.83 minus half of the distance, that is 400 by 2 is a h distance, plus the moment of inertia of this rectangular plate, it's b dq by 12 plus a h square. H is nothing but from here to here it is 119.17 plus 16 by 2 whole square. So this is IZZ. Similarly, get the value of IYY. Of both the sections, it is 39,202.6 plus dBq by 12. It passes through the centroidal axis of the rectangular plate. Therefore, it is dBq by 12. D is 16. B is 500 cube by 12. So I minimum is 512.4 in 10 power of 6 mm to the power of 4. Then get the radius of minimum radius of gyration. It's 157.76 mm. Then we can calculate the slenderness ratio. It's equal to 34.86. For the built up section, we always refer, as I said earlier, 9C of the table, 9C table from the code book. By interpolation, get me the value of FCD for 34.86. For the difference of 10, it is 13. For 4.86, how much? It's 204.68 Newton per millimeter square. The load carrying capacity of the section is 4,213.58 kilonewton, and the allowable load divided by allowable load, safe load or working load, whatever you call, for that you divide this ultimate load or the factored load by partial safety factor of 1.5, you'll get the safe load. That is 2106.8 kilonewton. Let's go into the last problem of this session. Now let us move on to the last problem of this session, where you have been given with 4 I section to be joined together of size 80 by 80 by 10 mm, which has got a height of 5 meters, hinged at both the ends. Effective length has to be calculated for this, and the cross section of the column is 360 mm by 360 mm. You have to find out the minimum load carrying capacity of the column. We have taken the column of 80 by 80. We have made the frame of size 360 by 360. Either it could be laced or batten. He said laced. And design of lacing we already studied, or we know it from the lacing system. Note on the properties of one angle section, ASA 80 by 80 by 10. For the 10 mm thickness, 80 by 80 is the designation. Look into the designation of that I section. For 10 mm, the area is 15.05 centimeter square. Then the radius of gyration, the centroidal distance of this axis is at 2.34 both in ZZ and YY direction. So you note on that value. And looking into the table, note on the value of moment of inertia of this section about ZZ and YY, which are equal for the single angle section. The end condition, it is said that at both ends are hinged, therefore effective length is equal to actual length, and you get that KL is equal to 5 meters. IZZ about the built up section, we have to take the built up section here. both x-axis and y-axis. Transfer the moment of inertia about the individual axis onto the built up section by applying the parallel axis theorem. So it is 4 times. The moment of inertia of the single section is 87.7 into 10 power of 4, which lie at the distance c y. Apply the parallel axis theorem. It is 360 divided by 2 minus the c y value will get me about y axis. If the same thing could be done on z axis. And all these things you know very well from the first year itself. Get the minimum radius of gyration, the slenderness ratio lambda, it's 31.56. Looking into the table, bucking class is as usual C. Now for 31.56, what is the value of FCD? FCD is 208.97 Newton per millimeter square after the interpolation. Get the load capacity. It's 1258 kilonewton is the load carrying capacity of the member. Now you understood the different types of sections, how to analyze. Same type of problems could be designed. We'll see that in the design section or the design session. The next coming video will be on design of compression members for the column section. Thank you for watching the video. If you like it, please do comment. And if you are not subscribed yet, do subscribe now. Thank you once again.